starter on rates of reaction. We said in the question, if you increase temperature, you increase rate of reaction. Okay, and that's a key important point you would need to know, be expected to know for your energetics or for your rates topic. Sorry, and we have people saying that you got the reason for that is you got an increase in kinetic energy. By the way, if you want to make a note of this, this is the sort of stuff. This is the way you note your answer. So increase of kinetic energy, and the increase of kinetic energy causes there to be an increased frequency of collisions. Right, that gets most of the marks. That's all good stuff, and I like it. But the answer we were attempting over there, all we need to say, and I'm just going to say this for you, and some of you wrote it, and some of you didn't. There's no change to the activation energy. All we need to say is, because the particles have more energy, the collisions are more likely to be successful. That's all it is. So it's just like bumper cars. If two bumper cars tap each other gently, no issue. If two bumper cars smash into each other, you're going to start getting sore necks and things like that. Okay, you're going to start to get reactions taking place. Chemical reactions involve things smashing into each other, causing bonds to break, and that allows new bonds, which happen maybe to be more stable, to form. So it's all to do with how fast, how hard those particles smash into each other. And that's the second point we need. And then I'll turn it into the year 12 answer just for your sake as well. So increased frequency of collision. So, and the increased energy of collisions means that a higher proportion of collisions successful, or likely to be successful. Okay, so big smash in, more likely to be successful. Notice points 3 and 4 there are separate marks. The explanation for temperature change causing increase of rate of reaction are separate points. So let's get that detail right. Your year 12 answer, this is what you don't need to know this, but if you want to know a little bit about what year 12 chemistry is like, we do a little analysis like this. So we say, please don't draw this and think you have to learn it. Okay, we do a distribution plot of particles with different energy. So not much energy, lots of energy. And this is just a frequency plot. So what the particles, some of them have lots of energy up here, some of them hardly have any energy, most have a kind of medium amount of energy. You've done histograms and all that in maths, I guess. And if the activation energy is here, you can see that these particles here, or these collisions up here, have enough energy to overcome the activation energy. They have energy greater than the activation energy. If you increase the temperature, you pull this whole chart to the right, and the particles, or a greater proportion of the particles, have energy greater than the activation energy. That's all it is. That's what's going on really, and you can start to study that at a quantitative level if you get to degree level as well. But that's completely IB level and A level stuff that you don't need to worry about, and I'll explain much more carefully and in detail at the time. But since you were trying to get there, I thought I'd finish it off a little bit for you. All right, so let's move back to the quantitative stuff. Last time we spent some time on percentage yield, and we learnt the percentage yield is actual yield, in other words, the mass produced from the reaction, divided by the theoretical yield, this is what you calculate using the reactive mass calculation, times by 100. That's what we did last time. It's already in your notes, you shouldn't need to write that down. We started working on the worksheet in class, and I think I asked you to finish that at home, but I'm not convinced I did. I'm going to ask Jude. Jude's shaking his head, so I didn't ask you to finish that at home. But you did certainly do 2 or 3 in class. So what we'll do shortly is finish those off. Not right now. We're going to teach you something else first, so you can go at your own speed. Okay. Before we do that, I'm going to ask you to tell me, without you looking up, what the reasons are. If you can remember what the reasons are why things might not be 100% yield. So you just remembered that there are three main reasons, or two main reasons, that yield is lost: either side reactions or reversible reactions, possibly also transfer, loss of material during transfer or during purification. All right. Before we go back and practice those, what I'm going to do then, so I'm going to teach you a concept called atom economy, and I'm going to teach you it using just lined paper. So you might want to make a few notes on lined paper, and then we'll refer back to the worksheets in a bit. So atom economy. So atom economy is a kind of funky technique, a sort of slightly strange thing they want you to learn, which is a way of analysing how efficient a reaction is in terms of waste. Okay, so let's consider an example reaction, a reaction which is done on an industrial scale, one that you've seen before. It's a reaction I referred to quite a lot. So let's imagine we're using carbon to convert iron oxide to iron, which will generate carbon dioxide. Okay, if we to balance that, stick a 2 there, 4 there, 3 there, and 3 there. An equation we've seen a few times before. What's happening to the iron during this reaction, please? Tell each other. It's getting 3, 2, 1. Ooh. Okay, so it is a displacement reaction, yeah, fine. But is it being oxidized or reduced? Reduced. So it's reduced because it's losing oxygen. It's also getting reduced because it must be doing what as well? Reduction is gain of electrons. It's gaining electrons, right? Okay. And carbon is being oxidized, right? Because it's gaining oxygen, right? And you're right, it's a displacement because which is more reactive, carbon or iron? Carbon. Yeah, carbon's more reactive. We know that because carbon is displacing iron from the compound. I'm just using chances to remind you of stuff you should know anyway. All right. So if we're making iron from iron oxide, we don't want to make carbon dioxide. We regard this as a byproduct. All right. So this is waste. This is stuff we don't want. And if you have byproducts as an industrial chemist, you've got to find ways of disposing of them. It could be that you dispose of carbon dioxide by pumping it into the atmosphere, but that's environmentally damaging. Or if it's a solid waste material, you might have to dispose of it by landfill, and all that costs you a lot of money. So industrial chemists want to make things that have limited waste. So essentially, it's a measure of efficiency, and particularly refers to waste, but it does it quantitatively. Okay. The way that percentage atom economy is determined is that what we do is we look at the product, the desired product. The desired product is iron. That's what we're trying to make. That's what we can sell and make a lot of money. We work out the relative mass of iron in the product. So there are 4 iron, or 4 moles of iron produced. If we look at the periodic table, iron's got a mass, or a mass number of 56. So 4 lots of 56. And we do that as a percentage of all of the products. And which is 4 lots of 56 times 3 lots of 44. And you times that by 100 because that's it's a percentage. So if someone could just tap that into a calculator for me with care, that'd be helpful. So it's 224 divided by whatever that lot is.
What would you call iron? Is it the product?
Desired product. Desired product. So 224 divided by 356 divided by 100. So I haven't worked that out yet. Which is 60, more or less 63%. Okay, so 63% atom economy. In other words, 37% is waste. And that calculation they'll ask you to do in your exam. More than likely you'll get that in an exam. Okay? And you could compare the atom economy of making iron using a slightly different approach. You're still using iron oxide, but instead of using iron you could use carbon monoxide. That would still make carbon dioxide and iron, but the balanced equation is slightly different. So let's work out the atom economy for this related reaction. Iron is still the desired product, so it's 2 moles of 56 divided by 2 lots of 56, add 3 lots of 44. Look what I'm doing, I'm deliberately writing all of the numbers for the examiner because I want the examiner to give me all the marks. So over 244 times 100, and if I've done it right on my calculator here, I've got a pretty nasty calculator, but I've got 46%. So can you see those two methods give different atom economies? Now I've got a few things to point out before you start doing questions yourself. I'll just give you a chance to write this down. One thing I want to point out is that something you already know, which is the mass of the product is of course equal to the mass of reactants. That's the law of conservation of mass. And so when you look this up in your revision guides and textbooks, the denominator of this equation might be written as the total mass of all the reactants, but of course it's exactly the same, isn't it, as the mass of products. The other thing we need to consider is the other factors that industrial chemists might take into account when deciding which is the most efficient approach, this one or this one. They might consider atom economy, but I want you to think about now what other factors they would consider. And we can brainstorm those now. So I'll hit pause on the video. We'll brainstorm them and then write them down on a worksheet. Okay, that's it. So there was nothing wrong with what I did in the first place, but people have managed to convince me that I was wrong, which is quite brilliant of them. If it wasn't clear, the 44 here is the formula mass of carbon dioxide, and that's where that came from. So if you weren't clear about the 44, so I'm sorry about that. So some of the factors you might consider would be the cost of the reactants, the availability of reactants, environmental impact, toxicity, energy requirements, time it takes, and the yield of the reaction. All might be things to consider. And when you get to the worksheet, which is entitled Atom Economy, which you'll get to in a second, you'll see on the second page of this, it's got that exact question there, which is identify other factors which should be considered. Right, can you have a go at these ones here? I'm going to do question 2 here on the board so you can see me doing another example. We've already done question 3. Can you do these on your own? Have a little go, please, yourselves. And once I've done question 2, I'll stop the video and we'll carry on afterwards. So aluminium, 4 lots of 27. Divided by 4 lots of 27 and 3 lots of 32 times 100, and that comes to 52.9%. Well, okay, so as I say, the chance. Thank you. The chance of this particular skill coming up in exams is relatively slim. It comes up now and again. It came up last year, and it was worth a mark. Okay. Weirdly, it's not in the textbook, but it is in the specification, so we do need to cover it, and we're going to cover it now. We won't spend long on it because it's so easy. You can work it out without having been taught it. I would say. A couple of people not listening. I want you listening in. Right. So. You know that when we write out equations, let's say the one we've just done, for example, like iron oxide plus carbon monoxide goes to iron and carbon dioxide, we can write the reacting ratio underneath, and we use that in our equations, right? You don't need to write that down particularly. But how would you get to those numbers if you didn't, how would you get to those ratios, those coefficients, if we didn't have a balanced equation? The answer is you can use the mass data given in a question. So, for example, in question 1, which has been done for you, you're told that 140 grams of nitrogen reacts with 30 grams of hydrogen. All you've got to do is find out the number of moles of each, which is 5 to 15. So it's a 5 to 15 ratio, and you convert that to a whole number ratio by dividing by the smallest number, which is 1 to 3. And that's literally it. It's a 1 to 3 ratio. You won't even need, in these questions, including the one last year's exam, to work out the balanced equation. But I'm going to do it anyway because it makes me feel warm and fuzzy inside. Okay, I'm going to do question 2 with you. So you're told to work out the number of moles of butane. So number of moles is N of butane, which is 5.8, divided by the formula mass of butane, which is 4 lots of carbon and 10 hydrogens, 58. Whoops, 58 is equal to 0.1. And the number of moles of oxygen is 20.8 divided by 32, which is 0.65, I think. And so there's a 0.1 to 0.65 ratio, but it wants a whole number ratio here. And so first of all, I'm going to divide them both by the smallest number and get a 1 to 6.5 ratio, which is the same as the 2 to 13 ratio, and that's the answer to that question. That's literally what you've got to do. Hopefully you can see what I've done there. So it's 0.1 to 6.5. I've just times it by 10 to make one of them number 1, and then scale that up to make it 2 to 13 by timesing them both by 2. I'd like you to do the rest of the questions 3, 4, 5, and over the page 6, 7. Please.